We will do two examples to better understand how stress concentrations work. So in this example number one, and please feel free to pause the video and take notes on the description for this problem. We want to determine the maximum theoretical stress and the actual stress, considering the stress concentration factor for the following loading case. Now, what you should know is when you're talking about the actual stress that you have to the actual stress, when you're talking about the actual stress, is talking about the stress after you multiply your your stress concentration factor. Okay, in this case, I only have a purely axial load. So you have to go to your tables A15 to see what are the charts there. These are the theoretical curves, stress concentration curves, by the way. And you have to look what this nominal or theoretical will be. Okay, so sigma xx nominal in this problem is the area is given by this guy over here. Okay, so that would be the total load divided by W minus D divided by T. I always look at the table chart, and the chart will tell you what the A is. So that's the A you need to use in the analysis. Okay, so in this particular example, you have what your W is. Your W is 2, so this would be 5,000 divided by 2 minus the diameter, that's 1/4. And then the thickness is a quarter inch thick as well. Okay, and you can see that you have to go to the chart and find what best works for the condition you're doing. This is a flat plate, it's a bar basically, and it's that you're stretching it. Okay, so this is the case that you will use. So if I was to calculate this whole thing and I multiply, I can show that this gives you 11.43 KSI. Okay, after you do the math, you can show that. Okay, so this is what your nominal stress is now. Okay, this is your nominal stress. And this stress will actually go inside here. Now we need to find what your stress concentration factor is. To find your stress concentration, know that I need D over W. Okay, D over W, and D over W in this problem would be this D is a quarter inch divided by the total width, that's 2 inches, okay, and that gives you 0.125. Okay, I only have one curve, so I go to the table and I did this. This is 0.125. And when you find this value approximately, this value intersects there. This is 2.7. So you could say, this is eyeballing everything. So you can say your KT is approximately equal to 2.63. You may wonder where I got that value. Well, I got that value from the exact solution. Okay, so I know what the equations are. They're given in tables. But if you were going to eyeball it in for your purposes, you could say this is 2.63, 65, and that would be okay as well. So as you move on, then your new stress that you will use in your calculation, this is what goes in your state of stress. This is in state of stress. This is what will go inside your state of stress. This is KT times K axial, this is the nominal or theoretical, that would be 2.63 multiplied by 11.43, and that gives you a value of 30.06 KSI. So you can see that the factor is almost, it's almost by 3. So this is 11, you're getting 30. So this is the stress that you have to use in your calculations. Failure to do that, then you will have, if you fail to use the stress, you're going to have a model that's not entirely correct. And if I'm going to do this, and just to explain what's really going on here, um, you have something like this. If I want to really the location where this is happening, this is an axial bar, so all the stresses are the same. The location can be anywhere here or anywhere there. That's where I'm calculating this sigma xx max. Uh, Typically, even if you're working with your stresses here, right? But we know if in the case that you had bending, correct? And you say, well, I know that the stress is here. They don't have the stress concentration factor, but just it's a common practice just to assume that these stresses are actually not only applied here, but they extend through the whole cross section. Okay, so that's very common to do as well. Okay, so this is example number 1. Let's move to example number 2. This example, we are working with a rectangular fillet bar. So it's a bar, if you think of, it's a rectangular bar, so it does something like this. Okay, it's a rectangular bar. It's a rectangular bar and has a fillet of 13. This is right in the middle, and it has a fillet radius of 0.13 millimeters. Everything is in millimeters. Just remember that Newton's millimeters squared actually give you megapascal, so that's gonna nice neat properties, that a property to know. This is you have an axial load and you have a bending load, and you ask to find the maximum bending stress in this problem. Well, in this location of interest will be obviously this location right here. And although we are calculating what the stresses are happening here, we will use this dimension to evaluate everything. Okay. And once again, these are the tables associated with this case, and you have to go and see what these guys are right here. Okay. These are the areas that you will use here in your analysis. Okay. So if we were to do this now, first of all, I need to know what my R over D is. R over D is 13 over 114, and that gives you a value of 0.11. Also, I need the value of big D over small d, and that's given in the problem, 1.5. So I have this, and I can go to the table, and I can find what this your stress concentration factors look like. Here, I would say the stress concentration factor is, in this case, for the bending case, this will be approximately, this is 0.6, this is 0.7. So you could say this is more or less 1.75. Here you could say the value here is this is 2, maybe 2 point, you could say 2 point, this is 2, this is 2.1, So you could approximately say that's actually equal to 2.1, or if you wanted to be a little bit more accurate, you could say this is approximately equal to something like this. This will be in bending, as you can see, and this is in axial. Okay. So if I was going to calculate this now, and I did these calculations, first of all, here, I need to know what my I is. Your I will be your T D cube over 12. So if you replace those values in there, you find this is 12. You find this is 114 cubed divided by 12. That gives you a value of 3,086,550 millimeters to the fourth. Your value of C is 57. That's D over 2, by the way, millimeters. So from here, your value of Z will be I over C, and that gives you a value of 54,150. Okay, so that means that your actual stress, your nominal stress in bending, your nominal, will equal to your moment applied divided by Z, and that gives you a value of 4155. Then same thing here, the area has to come from here and tells you what the area should be. The area is D times T, and that would be 114 multiplied by T, that's 25, and that gives you, this is millimeter cubed, by the way. So this will give you a value of 2,850 millimeters squared. So your axial stress, nominal axial stress, will be your load P divided by area, and if you evaluate that, that gives you 2.0 KSI. I'm sorry, this is all megapascals. Megapascal and megapascal. Now I have to take this and I need to multiply by with these factors. So sigma XXA will be KTA, sigma XXA nominal, and that will be 2.05 multiplied by 702 gives you 14.39. Sigma XXB will be KTA multiplied by, B nominal, and that will give you 1.75 multiplied by 41.55. That's going to give you 72.71. This is all megapascals. And then what goes inside your state of stress is sigma XX is sigma XXA plus sigma XXB is equal to, and I'm going to add these values, 14.39 plus 72.71, and that gives you a value of 87.10 megapascals. So this is what would go in your state of stress for sigma XX. You have to just pay attention that you are actually multiplying now by stress concentration factor before, these are the modified values, and you have to do that before you add that to your state of stress. Okay, this concludes the two examples.